Thank you very much, Allison. Thank you very much, everybody, for joining us. My name is Jeremy Barton, and Eric has provided an amazing vision over the last 40 years. This is the longest lever anybody's ever thought of to change the world. We need to build that lever, and then we need a place to stand, maybe a fulcrum. He conveniently cut out most of my need for slides for motivating the long-term vision here. Thank you very much. Everybody else gets 7 minutes. My first draft of this would have been a 6-hour talk and would have involved you murdering me very quickly. So my version of molecular machines is we're trying to steal all the principles we can from biology in order to build technical platforms that we can use to solve problems that maybe biology can't, and that we can use to really advance the technical capabilities of our species to solve major problems that currently are intractable. Chemical separation, that applies to building fast drugs more quickly, more cheaply, CO2 capture out of the atmosphere, etc. But building molecular machines by itself is pointless, right? Our job is to facilitate other people solving their problems. We're building tools, and we're making it easier for major science problems to be solved. In the long run, the vision is basically build anything, anywhere, cheaply at scale with minimal waste. That changes the economic structure of our species. That is worth more money than exists in the world today by large multiples. But in the short term, our job is to help other people solve their problems. I'm going to give you a little bit of a personal journey. I have been in this field longer than most people here, but not as long as some. This is me in 1994, when on the nascent internet, I stumbled into the idea of molecular machines. Unlike most people here, I did not start with engines of creation. I've started with sci nanotech and the arguments of what you could do if you had this kind of technology. And the discussions were quite impressive. You go from utility fog, devices that you could use to make balsa wood scale anything kind of stuff, to space elevators and space construction, to medical nanorobotics. Everybody's saying, well, from first principles, this ought to work. If this works, what can we do with it? I particularly remember discussion on the power to weight ratio of micron scale ducted fans and allowing that to make it really easy to build flying cars. But we also ended up in the culture, right? And we started getting sci-fi visions of nanotech. And there was no plausible pathway to get there. Nobody knew how you build medical nanorobotics in 1994. And our culture had lots of people pushing our scientists. Hey, give me some nanomachines. You're manipulating atoms on a surface. You're going to get us some nanomachines. And that built a social stigma into this because nobody knew how to get there. And they pushed back. Don Eigler, not a fan. First guy to manipulate atoms. I decided this was something I wanted to be involved with, not the Borg, but the nanomachines. And so postdoc, moving along, we start to get some actual nanomechanical technology, right? Simple DNA nanostructures. This is not well time correlated, but you get the idea. And I wanted to be involved. So I've got a PhD in physical chemistry and an undergrad in molecular biology. I'm a generalist. After my postdoc, I end up in a stealth startup and eventually at Canadian Banknote working on atomically precise fabrication. A piece of the puzzle. I'm not in this picture, and I think David Lister is just out of frame, but we got $40 million from the Canadian government and a substantial program pushing forward on atomically precise manufacturing in Canada. Pictures get better and better, right? My job was to build the experimental program, all right? So I get to be on some patents, look at the title, look at the author list. You might imply that we had to do something with mechanosynthesis. That's the public information available. We were very secret, very quiet, and that may be changing. We've got some members of that organization here today. But in January, due to a strategic realignment at CBN, I and a large number of our team members left. We'll leave it at that. But now I get to make my own choices, and I like this picture better. I still had brown hair. I started going gray at 16, possibly be thinking about all of this. So in this time, in the last 20 years of working on aspects of these problems, getting the education necessary, thinking that I would graduate out of a PhD and go straight into something that was fully operational, and then having to build something from scratch, I've come to a certain set of personal conclusions on molecular machines. And the first one is this is not an epiphany-based discovery process. There's no one weird trick that will give us nanomachines. There's a lot of work to address a lot of problems to build a technical platform out of these principles. And it's going to be a system of capabilities working together. Socially, in large part because of some of that early pushback, we have thousands of scientists and engineers around the planet working on nanomachines who don't call it that, all right? We've got, what, 4 separate communities here in this room, all of which working on nanomachines, and not really working together. They're separate communities. I believe if we pull things together, we collect all the capabilities everybody's working on, we wrap a common unique language around it so that we are all not constantly changing our terminology, and we're all presenting the same language, the grant funders and the administrators and the CEOs of the world, we're going to be moving a little bit faster. And as Eric pointed out, moving faster, saving a month, saves, makes a lot of money, but saves a lot of lives, because the tools we're building, one of their high impact areas is for medical diagnostics, medical intervention. But to really pull this off effectively, I think we need to be more organized than we are right now. Towards that end, I'm founding the Institute of Nanodynamics, an independent research and development effort. This is not corporate. This is a 501c3 public charity. If we need to coordinate efforts and all of the big centers that we build at universities turn into all of the PIs taking their money and scattering to the 4 winds, maybe universities aren't the place to do this. If we do corporate development, and for IP reasons, we try and keep everything secret, we push forward on particular pathways and we never talk about it, we only explore a tiny fraction of the available space. I think we need to be pushing forward in a coordinated fashion and with more than one research institute focused on building the field of nanomechanics, nanomechanical engineering. And so with the acronym I've picked at the moment, ION aims to help. To start with, we're taking a systems engineering approach. Right? We want multiple methods to build the technical stack necessary to construct useful nanomachines. Whether this is out of protein, DNA, diamond, pick your thing. We want to make sure that the basic foundational technology to build nanomachines that solve problems is available in open source as a public benefit. And then people will build companies on top of that, and other people will build companies that make a better version of the tech stack, and we'll eventually end up in a giant race to self-replicating nanobots, much like the AGI race today. But if we try and do this privately, we're not going to get there. Or if we do get there, it will be later and it will cost millions of lives. So the Institute is not just a granting organization. We're going to build a lab and a team. We're going to do that interdisciplinary research in-house, and we're going to work with the community. We're going to foster projects in order to push forward. We want to do this open science, and we want to do this in full connection with the broader community. One broader community, not 4, not 5. This is a field building exercise in addition to a research exercise. Our job is to put everybody working focused on hard problems from different disciplines basically in the same room for the 6 months it takes to realize that you've been arguing over semantics rather than technical content. And then take that semantic realization and put it out into the community so that everybody can more effectively collaborate with each other. I mentioned project sponsorships. We can't do everything in-house, nor should we try. So we will be working with academic departments and companies and whatnot to sponsor specific projects that look like high-value opportunities in the space. We'll be hosting students, postdocs, and in the framework of MSEP, gifted citizen engineers. Our objective is to build this field, and more minds give us more progress and help us solve more problems. Finally, there's a community building effort linking the people who need the nanomachine, the capabilities that nanomachines can bring to the world, with the people who can provide for those needs. We get the neurobiologists in. We're not just going to be hosting postdocs from molecular machine groups, but also postdocs from carbon sequestration or longevity, people who plausibly should take a sabbatical to learn about these new tools that we're building. And finally, since we're doing an open science work to publicly build nanomachines, we're going to have to engage with the public. There are thousands of engineers working to build nanomachines all over the world, one way or another. But there are millions of people all over the place who are wondering where nanomachines went, who got the promise and the peril, or who saw something like Generator Rex in high school, where we've got cartoons that have magic nanomachines changing the world. We're gonna have to walk them back from these sci-fi visions and put them into, here's what the real world can do now, here's the next step, here's where we think it goes in the long run. But that's a vision that if we put a plausible pathway in front of them, everybody I have ever talked to wants to contribute to, including the owner of a Magic the Gathering card shop I ran into 3 days ago. The public wants this. So Eric yesterday put up the classic product value capture research cycle and included his triangle that had the vision and the visionary philanthropists kicking the whole thing off. The Institute of Nanodynamics is, oh, that should not have gone, is approximately right here. Hopefully that circle is over the arrow rather than off to the side. Literally, I'm founding this right now. We're signing incorporation documents shortly. I've got a board of directors. It took a while to get everything lined up from an organizational standpoint. So we're at the point of seeking visionary philanthropy and funding. Now in the process, I've been speaking to a lot of people. I've talked to many people in this room. That's part of why we're here. But I've also been talking with certain government funders. I've been talking with a variety of people with access to potentially visionary philanthropists. There's an enormous amount of interest in this. Perhaps they go to Magic the Gathering card shops. If we have a plausible pathway to build synthetic, useful, and productive nanomachines, the vision's been embedded in our culture for decades. People want this. So your skepticism, and I sense the skepticism, is healthy, and it should be about, can we get the money? And then can we execute? But that's where we're at right now, and that's the objective. Let's build a spiritual home for an interdisciplinary, integrated effort to build nanomachines so that we can all work together and so that your postdocs and students have someplace to go if they don't want to be professors and still want to stay in the field. But today, since we don't have enormous amounts of funding, hundreds of millions of dollars to build a lab and hire a team, our focus is on the systems engineering approach to deliver multiple pathways to nanomachines in public. First, we've got a scope question, right? Are we going to be building self-replicating nanofactories that change the economy? But it's out of scope. I end up dividing our nanotech into several phases of development. So this is my personal opinion. But first, we've got what Eric called the dumb nanoparticle level of nanotechnology. This is the nanomaterials community that, when there was no plausible pathway to nanomachines, basically took the nanotech funding and did amazing things with it, right? As dumb as these are, this is nanostructured electrode for lithium-ion batteries. These are going into our power grids now. These are what are helping us leverage solar and wind to get carbon out of our power infrastructure. This is a result of the nanomaterials research. The nanoelectronics in our computers are a result of the nanomaterials research. Good static nanostructures have changed our world already, created enormous value in our economy. We're pretty good at it as a species. Next, I think it's time to design, build, and measure atomically precise components and structures. And we're pretty good at this, mostly because synthetic chemists can do a pretty good job, and biologists have existing productive nanomachines we can leverage to make atomically precise components, DNA, proteins, etc. We're starting to get to the point where we can do artificial structures. So here's the carpentry example Eric put up yesterday. And we've also, in scanning probe microscopy, done things like this. And this is taking a reactive polymer, using a scanning probe microscope to remove a capping group, in this case a bromine atom, exposing a radical on the surface, and then picking up a C60 and interacting with that radical, making a chemical bond and pulling away. This is what Eric was talking about during the Smalley argument. right? Rick Smalley got up and said fat and sticky fingers mean you can't control chemical reactions because he was picturing a different kind of chemical reaction. And Eric was saying, yes, you can, because you can do something like this. But we didn't have a public demonstration of that. That was an in-principle argument. We now have public demonstrations of mechanosynthesis, all right? What this means is that the kind of positional chemistry that biology does in order to build nanomachines is not unique, is not uniquely special to proteins and DNA. Positional chemistry is a thing. If you can control how your reactive groups come together and enough of the environment to make sure that they react there and only there, you can build atomic structure. That's the principle that gives you the diamondoid nanomachines that David was showing. This is the fundamental piece of science that says, look, the long-term vision is probably possible. The next phase is to assemble, control, validate, and use nanomachines. I make this one yellow because we're not very good at this yet. The people who can do this are the DNA nanotech community and a very small subset of the protein engineering groups. But this is where the obvious potential is right now, right? Taking atomically precise components, putting them together into mechanical structures, actuating, driving them so that they are actually machines, and measuring how they work. It's that measuring part that's going to be tricky. We've got a lot of biological examples, Baker Lab work from Alex Corvin, putting together a nanomechanical axle and wheel, etc. Taking atomically precise components and self-assembling them into nanomachines. The next phase, we build nanomachines to make nanomachines. We've got somebody who recently got out of the David Lee's group. We've got a couple examples of using rotaxanes and similar structures to try and control organic synthesis. But we're nowhere near to the point where we can make synthetic nanomachines that can make nanomachines. We can steal nanomachines that make nanomachines and use them, and we can cheat with ribosomes and DNA synthase, and we do, and we should do as much of that as we can. But the next real phase is, can we make artificial ribosomes? You can keep going. You can scale nanomachine production to the point where you can make megatons of stuff. If you're feeling particularly exotic, you can say we can extend the material capabilities and go beyond proteins or beyond diamondoid or whatever to build anything on the periodic table. You could go farther. You could say, well, early nanomachines will probably piss away lots of energy because we don't need to be out competing biology in order to make things that provide value. So our thermodynamic efficiency will probably be terrible because there's no reason to optimize the same way that biology has optimized the fitness function of every protein in your body over the last 3 billion years. But at some point, we're going to want to cut our energy cost for our nanomachines. And I'm sure there are future phases I've never given any consideration to. Narrow the scope. You can't strategize, you can't plan anywhere out there. So our focus is on these two categories: atomically precise construction of components and assembly, measurement, and validation of nanomachines. Let's get the world to the point where our citizen engineers can submit a design and have 5 or 6 companies available to actually print and build that design and tell you if it works. So, just to bring it back, why now? Right? Why is now the time to try and do something like this? And the science is there, right? We can make simple nanomachines. We can measure dynamics in certain systems. The problem we've got is that the systems we can measure dynamics in are not the systems we can build nanomachines in, right? But now is the time, but we have to take a systems approach. So, in my personal view, our next steps: integration and operating environment. Are there ways to take, for example, protein nanomachines and operate them in the environment where you can measure their dynamics? What does it take? Complex control. Can we do more than 1 degree of freedom? Right? Can we actuate a complicated machine? How do we control those? Measure the dynamics. Challenge in a lot of the biological systems is you can build 1,000 machines and then look at those 1,000 machines and estimate the statistical population of every portion. Let's see, how do I do this? Basically, everything occupies a local potential well in the energy surface, and you can confirm that the statistical population matches what you would expect based on your calculated potential energy surface. That's half the potential energy surface. You're not looking at the maximum. You're not measuring dynamics. Does your model actually work? you're only looking at half of it. We'll keep an eye on scale up because that's the next phase, but this might drive a few requirements. It's not what our focus is. But finally, these are systems problems. This isn't an epiphany. There's no one weird trick, right? There's 6 weird tricks that we might need to come up with, or 12, or 4. We have to figure it out. So systems engineering is a discipline about taking one big problem and dividing it into lots and lots of small problems. And you use a standard development cycle, right? Have an idea, build a thing, measure the thing, learn, iterate. For the concept of this workshop and the first division I did, I ended up with 4 basic categories for what we have to do to build nanomachines. We have to design and simulate them. We have to forge and assemble them. In this case, I'm using the word forge. It's not a long-term term. If we do decide that forge is what we mean by making atomically precise components, I will lose a bet with my systems engineer. But the point remains, we have to make atomically precise components and we have to assemble them into active devices, which we then have to actively actuate, and then we have to control. And there's a difference between these two. There's the physics you need to make something move, and then there's the signals and the processing you need to make it move controllably and do more than one thing. If we try to build all of the control systems into a nanomachine where all we have to do is feed it power and it does everything we want, we'll spend way more time in design and simulation and failure than if we can get multiple degrees of freedom of external control of these devices. And finally, and this is the hard one, measure and validate. We need to know that the structure of the thing matches what we intended to build. We need to know that it's been assembled the way we intended to assemble it. And then we need to actually actuate it and make sure that it behaves the way we designed it to. And we need to know that the input signals we've given it actually match the input signals in our model, that the environmental conditions match the environmental conditions in our model. We need to measure a lot of stuff because the first 50 times you build this, it will not work. And you will have to figure out why. And the more data you've got, the easier it is to figure out why, but you will not know beforehand what your key measurement is. And then once we've got them working, we cut almost all of those measurements out. You leave only what you need for the control loop. And then you update and iterate. So we're focused on model-based systems engineering. This is a technique developed at NASA to manage high-risk projects with high complexity. I personally, maybe I can keep 8 facts in my mind at the same time. There are lots of things you need to develop in order to put together systematic nanomachines. The other thing is there's a lot of bias in our intuition. My intuition has leaked in here. I like proteins, I like atomically precise components, I like electrical. Which means I'm already trying to solve the problem before we've defined the problem. So our objective is to define the problem in a solution-agnostic way. But everyone in here has a solution to that problem in mind based on your existing systems and knowledge. So what we're doing is a decomposition. We're saying not what are the various threads people have considered, not a report saying here's what 30 different scientists think will take to get us to different nanomachines. We're splitting it up in a different way. We're saying what are the design choices you need to make in order to build and validate a nanomachine, and then we're looking at each of those categories independently. So if you do that, you end up with a workflow that looks a little bit like this. Now, what material do I use? What is the environment in which I build my atomically precise structures? And how do I get the material into that environment? How do I actually do my atomically precise manufacturing? So there's the actual construction process, but that's a feedback loop. How do I apply the force necessary to reduce entropy in order to make atomically precise components? How do I control that so that I get the component I want? You know, this is a pretty easy example in biology. I throw DNA at a ribosome and then ATP gives me force. But that's one example. There are lots of them. And then validate that I've constructed the thing I intended to, and if you can, that it has the material properties that you want it to have for the device you're trying to build. How good is your model? DFT is great for quantum calculations, but extraordinarily expensive for lots and lots of stuff. So you probably don't deploy it across the board. You're going to be using a cheaper model for material properties. You don't know if it's accurate. And even if you're using DFT, perhaps you used B3 LIP instead of Omega X97 Bizarro. So your feedback with your simulation is here in your observables. The next step is one that most of us, took a long time to think about. Your assembly environment isn't necessarily the environment you built your atomically precise components in. So maybe you have to change environments. In biology, particularly protein engineering, this is an obvious one because your fabrication environment, every protein gets made in a big vat of bacteria, which you then kill and extract your protein. And then you do it with another vat for your other protein component, and then you have to put them together. Your assembly environment is not necessarily your construction environment. And then you've got the same feedback loop. What's the physics that assembles the thing? How do I control the structure? How do I get my assembled set of components? And then how do I validate that assembly? Maybe your carbon nanotube is electronic, and so is electrically conductive, so the flow of electrons in this thing during the assembly process is not something you modeled, and your end result doesn't match what you intended, what have you. These are get the observables and figure out how you can update your models so that you can do better next time. Finally, you have another potential operating environment switch. Just because you assembled it in phosphate buffered saline doesn't mean that's where the instrument that actually can measure the thing works. But perhaps you have to do something in order to make it work in that environment. Maybe you have to cross-link the structure so that you can deposit it on a surface and expose it to ultra-high vacuum and it still retains its structure, and what have you. Then you've got another feedback loop. How do I power the nanomachine? How do I control it on multiple degrees of freedom? How do I actually make the thing work? And then how do I measure its dynamics? And then how do I figure out where it went wrong and update the models and iterate? And then you write the report. At the Institute, we'll do this full open science and we'll publish the failures. In our program, each of these categories can have subcomponents. So here is the current batch of build materials we've pulled out of various proposals in literature for things you might make nanomachines out of. Each of these, you can go in and put technical detail, you can assign risks, you can extract it all into XML and do whatever you want with it. This is the platform that the defense industry uses for running complex projects. It's enormously capable, which means it's an enormously complicated user interface. They could use HP and the next step, once you've got those capabilities, is solution pathway planning. So say you assess the risks of 84,000 different techniques, and then you go through and try and path out what do you need to do for a particular build material into a particular environment, into a particular assembly environment, et cetera, et cetera, et cetera. Current combinatorics give me 580 billion pathways through this at the moment, and it's just going to go up. But the key point here is you've got a human assessment of risks, so you can try and identify the low-risk pathways through this. Institute objective is to find at least 5 pathways to functional useful nanomachines. And I don't care what those pathways are. I'm agnostic to the technology. I'm focused on the systems we need to build in order to implement those pathways and then actually doing it. But the risk component is really high importance. There's lots of ways everything can go wrong. If I design 5 and execute 3, I'm going to cross my fingers and hope that 1 works. The current model breakdown looks roughly like this, and we've only started casual path planning. This is incomplete. Not every technique you use is on here. This is where I want your help right now. And then, once we've got that full list, the fun begins. We all get to do solution path planning. The exercise of doing that path planning has value above and beyond planning out your research projects, particularly if you do it in an interdisciplinary collaborative group. Marco might recognize this basic concept. This is a heavily dimensionally reduced representation of your training in your discipline. This is your concept graph. This is the concept graph of the person sitting next to you. This is the concept graph of the person sitting next to them. DNA nanotechnology, scanning probe microscopy, protein engineering. We don't have a lot of overlapping language. This is why interdisciplinary work is really hard. And in 2-day workshops, we might identify that we want to build a nanomachine that requires these 3 concepts. And we have no idea how to talk to each other in order to actually identify and work that out. And in a 2-day workshop, maybe you do this. In the next workshop, maybe you do that. You make some links between your concept maps. And now you can actually talk to each other a little bit. Maybe you find that a concept from one field can be imported into another field, and suddenly you've got 947 papers because you've used a metaphor from somebody else's field to advance your own. And perhaps you discover that two fields are using the same, different words for the same concept. This is why interdisciplinary research is hard. It takes 6 months of focusing on the same problem to discover you've got a semantic challenge more than a technical challenge. This is why I'm not just trying to run a grant program. I'm trying to build a lab where we've got people who can take the output of these workshops and incorporate it into their plans and push forward. And where we spent the 6 months to a year to 2 years to fight through these problems and come up with a unified conceptual map of nanomechanics and nanotechnology, and put it out to the world and educated people and taken the new inputs and updated all of our collective learnings. And this takes time and proximity and focus. But the exercise of working through one of these solution planning efforts with somebody who is from a different field really highlights a lot of those miscommunication points. It's like, oh wait, you were thinking about this for that? Well, what about this other thing? Just the exercise of doing the path planning has communications value. So, our path forward as an institute. Well, today we're engaging with everybody and trying to learn how to talk to each other. We are going to build out and publish the roadmap. We're going to fundraise. If you've got any visionary philanthropists in your Rolodex, let me know. We're going to update this roadmap at least once a year. This is a living document. Plausibly, there are better ways to do it, and we'll have to discuss that when we have some money. We're going to be sponsoring risk reduction projects and key value creation. If it looks like the coolest thing that we can do to enable nanomachines are 3 different environmental transition technologies to get parts from different disciplines into instruments that you've never thought about before, we'll sponsor those. We'll work with you to develop those technologies, because it's going to take us 2 years to build a lab once we've got the money. But if we've got enough money to sponsor projects and work on grants, we can advance the field together well before I can have an interdisciplinary research group up and running in a new facility, which we'll be building. But collectively, all of us benefit by working together to build the foundation for a nanomachine tech stack. Because our job is to help people, right? We're building components that other people will use. We want to make sure that as many people as possible can use those components to solve problems. And we'll be sponsoring and incubating startups and whatnot in the time in the future. Final couple general points, because I've been preaching to the choir for a long time. Hammer this again. You're from different fields. Talk to each other. It'll be hard. It'll be valuable. Second, every time I came to one of these workshops or one of these gatherings before, I was in private, secretive corporate research. My objective was to find somebody here who could help me solve a problem. And in the process, I made a lot of shallow connections, most of which didn't pan out. When I pulled back from that and said, well, I have a lot of knowledge and skills that are not proprietary, how can I help the person next to me? I made a lot of deeper connections that actually panned out and provided value over time. So if you're here looking for somebody to help you, you will find them. But you will find them more effectively if you start with how can I help the person sitting next to me? All right? Keep that in mind. And finally, we're going to have a lot more influence if we build a coherent social structure of the field of nanomechanics. We've got MEMS, we've got microfluidics, we've got examples of interdisciplinary fields where they built community around a shared platform of tools and ideas. And in the process, suddenly all of the grant administrators and funding people are starting to get thousands of grants using the same language, rather than thousands of grants that look like a disparate, incoherent sense of what was going on. If we can unify our language, if we can say, I am working on nanomachines and I am focused on the control problems and that is where my work fits, and they are getting that from 1,000 different positions, and they've got a unified model to understand what the impact is, we're going to have a lot more influence than in a disparate, incoherent group of communities. The DNA people will be fine. The rest of us? So, final. In principle, this looks possible, right? All the bits and pieces, none of the science says this is impossible. And while there are thousands of scientists working on it, there are millions of people waiting for it. And the impact of what we can do is going to be amazing. But we've got to create incremental value along the way in order to actually get that economic flywheel going, which means we have to do the work, right? We have to do the work. We can't just rely on super intelligent AI to give us these nanomachines, because even if we had super intelligent AI, we don't have the facilities or the robotics for the super intelligent AI to actually implement any of this. And we really don't want it to, right? We have to be in the loop. We have to control our own destiny. We have to do the work. So this group of people is a nucleus of people who can change the world. And I encourage us to do so. And with all of that a little bit too serious talk out of the way, hopefully I didn't run too overly long. I believe we go into a discussion phase.
Yeah. Thank you.
Thank you.
Well,
I should stand up here.
get up there
All
because
right,
we're going to take questions, comments, red teaming, helpful suggestions before you're going to break out in just a second. Do you have a mic?
Yeah, it's over there.
Ah, great. Any questions, comments? That can be questions of understanding, can be questions like, why are you doing this? Can be questions like, is there a specific thing missing?
Yes, Brenda.
No. Well, then we, oh,
Brenda.
sorry, Brenda. Damn. Sorry.
Very nice talk. I was curious if you're thinking about specific types of nanomachines. So I mentioned this just because in my experience, sometimes motivating about a couple of specific aims can be quite helpful. And I feel like in the community, we're kind of doing a little bit of everything as opposed to targeting a few things.
So the scale-up requirement I mentioned kind of drives my intuition on it. I'm attempting to avoid imposing my intuition on the community before we do the process. But the high-value device I want is some sort of nanomachine, probably self-assembled, interfaced with external controls along multiple degrees of freedom that you can use to assemble atomically precise components into configurations they would not self-assemble into. Local minima. Most of our technology is local minima. Self-assembly gives us global. We can do better, but we'll have to nano-manipulate to do it.
Thanks for this presentation. So one of the things I've noticed in talking to people, and you mentioned it a little bit with the Borg in the beginning, it's not that people are unaware and need to be educated, but they're in essence educated already in the wrong way. And that's also a big barrier to them even listening in the first place. And so I'm just wondering if you've come up with ideas or just part of the scope of all of this to think of how do we try to undo all that damage that, say, Hollywood and so on has.
My focus is perhaps not the answer, but my approach would be focusing on what we can do in the next 3 to 5 years, right? Nanomachines, we can make DNA simple nanomachines. We can make some simple protein nanomachines. Hopefully we can interface them with more external control electronics so that we can make devices that solve these small number of problems, including making better nano devices. Focusing less on the long-term physical basis of the singularity and more on, okay, within the scope of what we can actually think about in the world that's changing so rapidly, here's where the impact is, and here's where we think the next level of impact is.
Show people things that work.
And ideally, show people things that work. Yeah.
If I may.
Yeah.
I'm up here in the low COVID zone. Another partial answer to that, I think we need multiple pressures on this because there's this deeply entrenched cultural confusion, is to have a vivid literal visualizations of advanced nanomachines, which still looks nothing like little bug monsters. They're things, we have a whole bunch of people, they're designing components, they're designing subsystems, they're designing systems, and there they are, and it looks like Minecraft, and the things that little people running around are not the things built in Minecraft. And if you have an actual, concrete, visual representation, explorable environment, and a lot of people who understand it will argue with you if you start talking nonsense, that's a situation where I think we're a couple of steps ahead. And that's one of the major goals for MSEP. That's a large part of my motivation, is to have a more clear view of the future that gets rid of some of the garbage.
Yes, and yet. People. And always people. But yeah, that absolutely helps. Having a visual depiction of what you're going for and being able to decompose it and actually design components and say, look, these things would work this way. And all of it together gives us a production system that operates in a pool of liquid xenon rather than in a Borg drone is incredibly critical for laying out to the world that, no, this isn't something that's going to cause accidents that will kill us all. It can't. We're going to get the flame wars. It'll be fun. But the other component is, I don't think all the models that we've got are right. And all the models that we can deploy in MSEP, they're not all perfectly accurate.
Why are you talking?
Shocking, shocking, I know. So having that physical organization actually updating the models and having the tight loop between the citizen engineer community and the professional science community saying, okay, you guys have designed these things, here's a model update, fix it, and we'll build some of them. I think that really adds additional social impetus to the whole thing.
Yes.
Okay, last call for questions, comments. Yep, yeah, if you wanna, this is just for the recording. So you still have to speak up.
Can you give a little bit of details about the software you used so far for the example of with the many orange boxes?
This is Enterprise Architect by Spark Systems. It is commonly used in the defense industry for systems engineering. It's a platform, it's basically a graph database that they've put some various UML and SysML languages on top of. You can use it to do a huge number of things, and doing it well requires actual skill, which is why I have a volunteer systems engineer.
Are you planning to run with this, or will there be special software?
In what context? For public
So
release?
is that a software that you can make accessible via web interfaces and stuff?
Not
or?
with any reasonable licensing. There are web interface ways to view into this, which we will be deploying and suggest updates. There's collaboration software that is on web interface for this sort of thing. In the long run, we'll probably need a custom stack because everybody always needs a custom stack.